Hi, my name is Timea Bezdan. I'm teaching assistant at Univerzitet Singidunum, and I will talk you about neural networks. So let me just switch my screen to the presentation, then we can dive into the content. So we will look at what is the logistic regression, what is the forward propagation, what is the cost function, why it is important, then what is the backward propagation, different type of the neural networks, and I will also explain you why it is called neural networks, so what is the analogy between the human brain and the artificial neural networks, and in the end of the presentation I will show you the actual implementation of the logistic regression in Python. So the logistic regression, that is a supervised learning algorithm, which is an algorithm for binary classification. Binary classification is a task of classifying elements of a given set into two different groups. For example, in image classification, a basic task is that we have two categories. For example, in this case, we had the input image is the cat, and we need to classify so whether it is a cat or a non-cat picture. So these two would be the two categories. And we need to look at the linear function. So that is the starting point towards the neural network. So as you can see, it is a quite simple learning algorithm, but it is a super important algorithm and function. So it help us to build up the entire neural network. And the linear function that takes the data as input, let's say it takes our cat picture from the previous slide, so we write it as x, so x is the input, and the another component of the linear functions are the parameter w. W is the weight or the connection weight, and the another parameter is the b, it is the bias term. So we need to add bias to the weighted sum so we can know how high is our weighted sum. And in the end, so we will get the result, that is the output. Output is y hat in this particular case. And let's say if that number is very large number, then it will indicate a large probability that the input image is being cat in our example. On the other hand, if the number is very small, so it would be indicate that the picture is a non-cat. And what we need to do with these outputs, so we need to map these values somehow, and for that we need to introduce nonlinearities, and we use activation functions, or also called transfer functions. In this case you can see sigmoid activation function. Sigmoid is a well-known activation function which pushes these numbers, that the output numbers, between the value 0 and 1. Then let's say if we got a large positive number as an output and we push it into this sigmoid function, then if it is large negative number, it will be close to 0. But on the other hand, if it is large positive number, then it's going to be close to 1. This picture, this represents the model of single neuron, which has input x1, x2, and x3, and these inputs are actually, it's corresponding to the number of input features of the data. And then you can see these arrows, these are the connections to the neuron, and this node, it is actually the neuron, or also called hidden unit, and you can see that inside this neuron we have two different calculations. First, we have the linear function, so we take the output of that linear function, then we will calculate the activation functions, and then we will get the output y. We have here the computation graph, and that can represent any function, and these rectangles in the computation are steps of computation that we go through in forward and the backward propagation. We will see more details about the forward and the backward paths in the following slides. We have three components to train neural networks. The first one is the score function, so that is the linear function and the activation function. Then the second one is the loss function, and the third one is very important, so that is the optimization. Here we have given x, that is the input, so our input data, and we don't have any choice over x, so that is given, but we have choice over the parameters w and b. And we are free to set these parameters in whatever way we want, and actually we want to set these parameters in such a way that this function gives the correct answer for every single data in our training data set. And we might get some terrible results, but that's actually the reason why we need to define the loss function, which will qualify how good or bad our algorithm is working. And we need to look for W's, so the values of the W, of the weight, that will minimize this loss function. And it will be set up in such a way that if we have a loss of very low numbers, even 0, then we are correctly classifying our data. But on the other hand, if we have very high loss, then everything is messed up and our parameters are not good at all. So we define the loss function, which measures how well the algorithm is working. Then we need to find an efficient procedure for searching throughout the space of possible parameters. And actually that process is called the optimization, which is very important in order to achieve high accuracy. For optimization, we use gradient, and where we just computing the slope, and the learning rate is the step in the direction of global minima. So we need to find those values for the W that will give the highest accuracy on our data. So we need to minimize and we need to find the minimum value of it. So in backpropagation, we calculate the derivatives in order to find the gradient of L, of the loss, with respect to the parameters, and to get it, we calculate it step by step. First, we calculate the derivative of the loss with respect to A, the activation, then the derivative of the A, of the activation with respect to Z, and here actually you can see that we have chain, so the A with respect to the Z, and the L with respect to the A. Then finally we will see, and we will need to compute how much we need to change W and B. Here you can see the representation of a neural network. You can stack actually more layers together, and on that way you will get deep, large neural networks. So you have the input layer, and as I told you, the number of the units or those nodes that you can see in the input layer that corresponds to the number of features of the input data, and in the hidden layer, so the number of the hidden layer and the number of the units in each hidden layer is actually a hyperparameter that should be tuned. And these arrows between these nodes, these are the connection weights, and you have bias in each node in the hidden layers. Then finally you have the last layer, that is the output layer. In binary classification you have only one node and the output is 0 or 1, so whether it is the given task or class or not. Here you have different type of neural networks. So first you can see the simple logistic regression that we see so far in the details. So you have here input, then you have only one node and you will get the output. Then on the right hand side you can see a neural network with a single hidden layer, and it is still considered as shallow neural network. So you have 3 input features, then you have one hidden layer with 3 nodes or neurons, and you have the output, and you will see the value of y hat. Then the third one, so it's bottom left, that's the neural network with 2 hidden layers, and it is still considered a shallow neural network. And finally on the bottom right you have a neural network with 5 hidden layers, and actually it's considered as deep neural network. And here is the brain analogy, so the biological inspiration for neural networks. So you can see the neuron, how it looks like. So it has like cell body, you have axons and dendrites, and in the bottom part you can see the neural network, the artificial neural network. And actually these dendrites in the neuron, these receives the input that come into the neuron, and in the middle is the cell body, which carry the information to these longer sides, to the axons, and the function of the dendrite is to receive signals from other neurons. In the artificial neural network it would be analogous to the weighted input. And the neuron, or the hidden unit, is actually the cell body, which sums up all incoming signals to generate an output. Then this output travels through the axon to another neurons. So the axon is actually analogous to the output in the artificial neural network. And that point of the interconnection between the neurons, that is actually the synapses. So you have these connections between the neurons. And here is the implementation, simple implementation of the logistic regression in Python. In first step, the packages should be imported. So we have two packages here, the NumPy and the matplotlib, I'm sorry, for the visualization. And then we will create an artificial data set or synthetic data set. Then we will do simple data visualization, and after that we will initialize our parameters, then define the activation function, the forward propagation, the cost function, backward propagation, so all these things that we were talking about. Then we will do the parameter update to find better values for our parameters, and then we will create the logistic regression model, and finally we will do the predictions. So as I told you, first we need to import these packages. Then we can create a data set by the library NumPy. So you can see it like mp.random.randn. And after that we will concatenate these vectors, and if we print out the shape, so you can see it that the X has shape, so you have two rows and 2000 columns, and for the Y you have 1 row and 2000 columns. And if we want to visualize, to plot it, so you can see how this data looks like. So this is an artificial data set, and our task would be to make a classification. So if we got a new number, whether it will belong to one or to the another category. Okay, so here is the parameter initialization. So we created a function, define parameter initialization, and we have one input, so one argument, parameter x. Then w is the weight, as we said, and b is the bias, and we are initializing randomly the values of w. So we said that x is always given, so we cannot change it, but for w we can select values whatever we want, but actually it is like randomly initialized. And for the bias we can do zero initialization, and the output, so this function would return the value of w and b. So if we print it out, so you can see in the next section that if we print out the parameters, so what is the value of b and what is the value of w. Then in the next step we are defining the sigmoid function, and we are defining the function for the forward propagation. So it has input x and the two parameters w and b. So we are calculating z, so with the linear function. So we are taking w and x, we have the weighted sum, and we add the bias. Then once we have the result of the linear function, we will apply the activation function. So if we call this function the forward propagation and we print it out, so you can see here the values of that. Next, that is the cost function. So we are defining our function to compute the cost. And if we print out, so in this particular case our cost would be 0.69. In the next step, the backward propagation, we are creating function for the backward propagation. It has two arguments, so it has a and y, so the activation, and the y is the output. Then we are calculating the values for the w and the b. So if we print out, you can see what is the value of w and what is the value of b. And finally, what we need to do, we need to update our parameters so we will get better result. So we create a function, update parameters, and we have w and b. So what is the values? Minus alpha, that is the learning parameters, times the values that we got in the previous function. And here is actually our logistic regression model. So we have the function logistic regression. It has input x, y, w, b, and we define the value for the learning rate, that is alpha, that's 0.01 in this case. We have number of iteration equals to 1000, and we have the loop, so we will iterate it 1000 times, and we are calling all these functions that we define. So first the forward propagation, then we are computing the cost, then the backward propagation, and finally we are updating our parameters. So once it iterates through 1000 of iteration, then we will see, we will plot the result. So here we are calling the logistic regression function and plotting the results. So you can see what is the cost after the first iteration and after every 100th iteration, and you can see how it is reducing the number. And for the prediction, so we defined our model. Now we can see if we add a new data, what will be the value. So we are creating this function predict, and it takes parameter x, w, and b. So we are calculating the forward propagation, and if the prediction of the activated output is greater than 0.5, so it will be the actually the output of this function. So then we can see here, if we add some new point, then what would be the prediction of our y value. Thank you very much for your attention. So this would be like short introduction about the neural networks. Thank you very much.